Today's topic is Lewis structures, and first we're going to go over the steps that you need to complete in an orderly fashion in order to develop a correct Lewis structure. The first thing you want to do is count up and total the valence electrons in your compound of interest. Then you want to draw a skeletal structure of your compound with the least electronegative atom at the center, although if you're dealing with hydrogen, that goes on the outside of your molecule. Then you're going to draw covalent bonds between the individual atoms. Each time you draw a bond between two atoms, you will use up 2 electrons. Then you want to distribute remaining electrons as lone pairs. The goal here is that the combination of your covalent bond electrons and your lone pair electrons, when you count them up in your preliminary Lewis structure, they should equal the number of valence electrons you counted up in step 1. Then you want to evaluate individual atoms for the octet rule. This means in some combination of lone pairs and covalent bonds, you have 8 electrons around your atoms. This does not apply to hydrogen. Finally, for the atoms where the octet rule is not obeyed, you can take lone pairs and transform them into double or triple bonds as needed in order to get a Lewis structure where the octet rule is obeyed and you still have the correct number of electrons in your structure. So let's take a look now at a specific example. Developing a Lewis structure for ammonia NH3 is a fairly simple exercise. First, we're going to count up the total number of valence electrons, which in this case is 5 electrons for nitrogen and 1 electron for each of our 3 hydrogens. This gives us a total of 8 valence electrons. Then we put together our skeletal structure with nitrogen at the center and start adding covalent bonds. Once we have our covalent bonds, we can put a lone pair on our nitrogen. And now is the point in time where we want to count up how many electrons we have actually used. 2 for each covalent bond, so 2, 4, 6, and then an additional 2 for our lone pair equals 8 electrons. So now we have a match between our Lewis structure and the number of electrons we counted up, which is a good thing. Next, we want to look at whether we have an octet around nitrogen. 2, 4, 6, 8. Yes, we do. So it looks like we're in very good shape for ammonia. Whenever you're developing a Lewis structure, you want to ask yourself, do the number of valence electrons in the structure you have developed add up correctly? And is the octet rule obeyed where applicable, in this case for nitrogen, but not for hydrogen? Now that we have developed a Lewis structure for the simple molecule NH3, there are some Lewis structure tips and tricks that can be helpful in developing valid Lewis structures. For example, carbon likes to form 4 bonds. The reason for this is it has these 4 single valence electrons ready to make bonds with other atoms. Nitrogen likes to make 3 bonds. Oxygen tends to make 2 bonds. And fluorine, as well as the other halogens, tend to make 1 bond. The logic of this becomes apparent when we look at how atoms come together and share electrons to form covalent bonds. For example, in the case of methane, we see how the 4 single valence electrons of carbon combine with the single electrons available from each hydrogen to form the tetravalent molecule CH4. Similar logic applies for water, diatomic hydrogen, and diatomic chlorine. A somewhat more advanced Lewis structure is that of carbon dioxide. As usual, we're going to count up our total number of valence electrons. In this case, 4 electrons for our carbon, 2 times 6 electrons for our oxygens, giving us a total of 16 valence electrons. Our skeletal structure will have carbon in the center, and we can add covalent bonds from carbon to our 2 oxygens. Then we can distribute lone pairs, ending up with a structure that looks like this. At this point, we can now count up the total number of valence electrons in our preliminary structure. 2, 4, 6, 8, 10, 12, 14, 16. So we have a match between our structure and the total number of valence electrons. However, we do not have an octet around carbon. We only have 4 electrons around carbon represented by these 2 covalent bonds. What we can do here is we can take lone pairs and we can move them. In other words, we transform them from a lone pair electron into a pair of bonding electrons. How's that going to look? Well, we simply move this lone pair and form a second bond that will give us a double bond. We do the same thing on the other side. We move these lone pair electrons and form a double bond between our carbon and oxygen. Now at this point, we have a good Lewis structure. We have an octet around our central carbon as well as our oxygens on the side. Perhaps clearer to see when you look at this structure right here. 8 electrons around oxygen, 8 electrons around carbon, and 8 electrons around our other oxygen. We can now turn our attention to developing a Lewis structure for a polyatomic ion. The nitrate ion has the formula NO3- and a charge of -1. In addition to performing the usual steps to develop a Lewis structure, we must also evaluate formal charge and any possible resonance structures. We start from the usual place, totaling up our valence electrons. 5 electrons for nitrogen, 18 electrons for our 3 oxygens, and notice the addition of an electron to account for the -1 charge on the ion itself. This gives us a total of 24 electrons. The skeletal structure has nitrogen at its center, can add covalent bonds, and then distribute our lone pair electrons. If we count up the electrons in this structure, we will see that it matches the 24 electrons counted up previously. We do have a problem, however, with this Lewis structure. We do not have an octet around nitrogen. We will do the same as we did in the example of carbon dioxide. We will take a lone pair and transform it into a bond. This gives us a double bond connecting nitrogen to oxygen. Now nitrogen does have an octet around it, as do all these oxygens. So this is a good Lewis structure, but we need to evaluate formal charge using a fairly simple formula. Formal charge for any individual atom equals its valence electrons minus any lone pair electrons assigned to that atom in combination with 1/2 of its bonding electrons. So in the case of this oxygen, we have 6 valence electrons, but in the structure itself, we have 6 lone pair electrons assigned to it, plus 1/2 of its bonding electrons, meaning 1 electron. So 6 minus 7 gives this oxygen a formal charge of -1. The same applies to this oxygen. Now if we evaluate nitrogen, we will see that if we take its 5 valence electrons, there are no lone pair electrons in this nitrogen, so this number is 0. 1/2 of its bonding electrons, it has 4 bonds with 8 electrons, so 1/2 of its bonding electrons is 4. 5 minus 4 gives us +1 for this nitrogen. Finally, for this oxygen, 6 valence electrons minus 4 lone pair electrons minus 1/2 its bonding electrons, or 2 electrons, gives us 6 minus 6 equals 0. Now if we write these formal charges in, we can see if the total adds up to -1. And in fact, these charges do add up to our -1. -1 minus 1 plus 1 gives us -1. Note that it is customary to put brackets around our structure and indicate the overall charge on this ion, which is -1. Now we can move on to resonance. Double arrows indicate the presence of another resonance structure, and all we have to do is move this double bond to different locations for each resonance structure. In this case, we have the potential to move the double bond 2 times, giving us a total of 3 resonance structures. One thing to take note of is that the resonance structures are a somewhat artificial construct. The true situation is that each of these bonds has some partial double bond character. So this bond and this bond and this bond actually all share some partial double bond character. However, resonance structures are still useful to describe our molecule. Now that we have looked at polyatomic ions and formal charge, we can evaluate a little more deeply the roles of carbon, nitrogen, and oxygen in Lewis structures. Carbon almost never carries formal charge and can be basically counted on to be tetravalent. In other words, carbon will form 4 single bonds, a double bond and 2 single bonds, or a triple bond and 1 single bond. Nitrogen and oxygen, on the other hand, may form an alternative number of bonds when they assume formal charge. Previously, it was noted that nitrogen tends to form 3 bonds and oxygen tends to form 2 bonds. However, in the nitrate ion, as we have seen, nitrogen has 4 bonds and a formal charge of +1. Oxygen, when it has a single bond and 3 lone pairs, will assume a formal charge of -1. Notice that no matter what, for carbon, nitrogen, and oxygen, the octet rule is always obeyed. Finally, we want to look at some octet rule exceptions. We know we can have an incomplete octet or an expanded octet. In the case where we have less than 8 electrons, hydrogen can only form a covalent bond with 2 electrons. Boron can be surrounded by 6 electrons, sharing its 3 valence electrons. And then if we look at an expanded octet, note that some elements can have more than 8 electrons around them. This is called an expanded octet. Elements in period 3 have something called an empty D shell. This allows them to expand their octet by using this empty shell to exceed the octet rule. This applies to elements like sulfur and phosphorus. Octet rule exceptions, as we just noted, come in the form of the incomplete octet and the expanded octet. Examples of the incomplete octet include molecules like beryllium dichloride and boron trichloride. The expanded octet, on the other hand, tends to involve third period elements like phosphorus and sulfur. Phosphorus can expand its octet to accommodate 5 bonds or 10 electrons. Sulfur can expand its octet even further to form 6 bonds with 12 electrons around the central sulfur atom.